Hello everyone, welcome to my videos on elementary differential equations. This is video number 4 for chapter 5, and the topic of the chapter is the Laplace transform. Let's do a quick review of what we have talked about so far. So here is a list of the properties of the Laplace transform that we have learned. So the first property is linearity. So if you have a linear combination of two functions or even many functions, then the Laplace transform is the same linear combination of the transformed function. Property 2 is about derivatives of f. So here it basically says if you differentiate the function f, it corresponds to multiply the transformed function by s and with some initial condition. Okay, and then there is a version for the second derivative. Then you multiply by s squared, and then you pick up two initial conditions for f and f prime at 0. And then this goes up to nth order derivative, and you have Sn times the transformed function plus these initial conditions of the lower derivative will occur all here. Okay, property 3 is a counterpart of property 2. Here the derivative is on the transformed function f prime, and that corresponds to multiply by a negative t of the little function ft. And the fourth one is the shift theorem. What it says is that if you multiply the function ft by an exponential function e to the at, then what happens to the Laplace transform is just a shift by a unit of the transformed function. Also here I collect a table of Laplace transforms, those we have computed. So we know the Laplace transform of a constant function 1, and of an exponential function, and of a polynomial, and the cosine, and the sine. Okay, so probably make an effort to memorize these, at least for the duration of this course. Now we will show that we can derive many more Laplace transforms based on these that we already have and the properties on the previous slides. Okay, our first example. So we will use the Laplace transform of polynomial. So Laplace transform of t to the power n equals to that, n factorial over s to the power n plus 1. And using that, we can quickly find the Laplace transform of the function e to the at times t to the power n by using the shift theorem number 1, that is multiply by an exponential function, and will just cause the transformed function to shift with the unit a. That is, wherever you just have s here in the transformed function, you replace it with s minus a. Okay, so really quick. And if you really want to find this by definition, you can go ahead and try, and you'll find out it's a very lengthy computation. Okay, our second example. Let's say we will start with the Laplace transform of a sine function. Sine bt, the transform function is b over s squared plus b squared. Again, we will look at the product of the sine function with an exponential e to the at. So you see that you can just apply the shift theorem number 1, that is shifting by a unit, and that is replacing the s with the s minus a. Okay, the third example, we will use the given Laplace transform of the cosine function, which is s over s squared plus b squared. And then the function e to the at times cosine bt would be the Laplace transform of that would be taking this and shifted by a unit, and that is wherever you have s here, you replace it by s minus a. So this s becomes s minus a, and this s becomes s minus a. Okay, so you see how quickly we can get Laplace transform of these rather complicated looking functions, which you know if you want to work it out, it would take quite some work. Okay, now let's look at a different example. If you want to find the Laplace transform of the function t to the power 3 plus 5t plus 2, how would you do that? Well, you can do with the linear property, that is, and you can take Laplace transform of each term and then add them up. And you can even take out all the constant terms. So this will become Laplace transform of t cubed plus 5 times Laplace transform of t minus 2 times Laplace transform of 1, where for all these three transform we know what they are. And then let's put that in. So this will be 3 factorial, which is 6 over s to the power 4 plus 5 times 1 over s squared, that's for t, and minus 2 times 1 over s, that's for 1. Okay, and next example is based on this example here, this result here. Okay, so if we know the Laplace transform of this is given here, and then we can quickly find the Laplace transform of this function multiplied by e to the 2t, right, by shift theorem number 1. So that is, whatever you have s here, you just shift 2 units, so you replace all the s here by s minus 2, and this is what we write down here. So this term becomes that, and this term becomes that, and this term becomes that, and we have s minus 2 in place of s. So really quickly we can find it. Okay, our next example, it's a little bit looks like a bit more complicated function. So the function is t squared plus 4, the whole thing, times e to the 2t minus e to the negative t times cosine t. Okay, so it basically looks like it has 2 terms, this term and that term. So we can take one term at a time. To look at this term, how do you find the Laplace transform? Well, you see that this is a product of a function times an exponential. So we can wait a bit for the exponential, we figure out the Laplace transform of this, and we apply the shift theorem for that one. Okay, so what we have. So, okay, let's figure out the Laplace transform of t squared plus 4, and then we can do for each term. So for t squared we get 2 over s cubed, and for 4 we get 4 over s. And then we apply shift theorem to work out the transform of this function multiplied by e to the 2t. That is, you would just take this function here and shift it by 2. So replacing all the s by s minus 2, and that's what you get. And then we can quickly realize this one. This is the Laplace transform of cosine with a negative sign in the front, and then in that transform we're going to shift -1 unit. That is, wherever you have s, you will replace it with the s plus 1. Okay, and this is what we wrote here. So I'll get s plus 1 over s plus 1 squared plus 1. So that is for the second term, and then for the first term we figured out here. So the whole thing will be just adding these 2 terms and these 2 results up. Okay, so this part, the first 2 terms, is for this function, and then the last term is for this function. Okay, so you see, for such a complicated looking function, and it just basically takes 2 lines to work out the Laplace transform. Okay, now we are going to take a few examples using property 3. That is, if you multiply the function by a t or a negative t, what you need to do in the end for the transform function is to take a derivative. Okay, example 7. Now we start with the exponential function e to the at, and its transform is 1 over s minus a. And then if we multiply the function by t, so t times e to the at, the Laplace transform of that would simply be the derivative of the transform function here times negative 1, right? And then you can differentiate this in s, okay? This you think it's a function of s, and then you get 1 over s minus a squared. Okay, so this example, we are computing the Laplace transform of t times sine bt. So we see that this multiplied by t will result in a negative sign and the derivative of the Laplace transform of sine bt, which we wrote here. Okay, then you just need to work out the derivative of that. You can use the quotient rule, and you will get 2bs over s squared plus b squared, the whole thing square. And then very similarly, we can find the Laplace transform of t times cosine bt by simply computing the derivative of the Laplace transform of cosine, which is s over s squared plus b squared. Okay, and this differentiation takes a little bit more work, and so I skip the detail. I assume we can all do that, and in the end you will get this expression. Okay, so I want to say that even though it involves a little bit more work to compute the derivative, still it's much less work if you want to compute the transform by definition, by working out the integral of t times cosine bt times e to the negative st dt. That will be really a lot of work. Okay, so still this saves us a lot of time, a lot of hard work. Okay, so that's all the examples I have prepared for this topic. And I will end the video here, and next time we'll look at an inverse transform. That is, if we are given a function capital F of s, how do you find out the function that generated that Laplace transform? Okay, so I hope to see you next time then. Bye bye.